First of all, thanks a lot, Agne, for accepting to talk at the CosmoVerse series. Agnes is currently a PhD student at the Max Planck Institute for Extraterrestrial Physics with Dr. Ariel Sanchez. And prior to this, she completed a master's degree at the University of Edinburgh with Prof. Catherine Emmons. And Agne research interests include understanding the information content of the full shape of anisotropic galaxy two-point correlation function, as well as exploring how it may be combined with two-point measurements from weak gravitational lensing. She's also interested in understanding and assessing how the constraints from the low redshift probes compare and interact with ones from the CMB measurements. Today, she will present assessing consistency in physical parameter space with the full shape of anisotropic clustering measurements. Agne, you can start, please, when you're ready.
Okay, so thank you very much for having me here. It's a great pleasure to talk about my work. And today I'm going to cover the work that's presented in 2 papers, and these are their archive links. And this is something that I worked on together with my supervisor, Ariel Sanchez, as well as Andrea Pizzotta and EBOS collaboration. Right, so let's start with the customary introduction about Planck being the cosmological standard or setting the cosmological standard. So as we all know, Planck's observations of cosmic microwave background radiation all the way back at redshift 1100 allowed us to obtain the most precise cosmological constraints to date and crowned lambda CDM as our standard model. However, as we all know, Planck provides predictions rather than measurements of what these cosmological parameters, what values they should take at redshift 0. And therefore, a great way to test our model, to test our measurements, is to compare Planck's predictions for low redshift universe with our actual measurements. And as you will all know by now, the reason why we're here is that we do actually see some tensions between these predictions and measurements. So first of all, more significantly, of course, we have the H0 tension, which is up to 5 sigma, depending on what data sets you compare with. And to make this, to describe this in a super simplified manner, of course, it just refers to the fact that Planck's predictions for the value of expansion rate today are around 5 sigma lower than what we actually measure with direct probes. Less significantly, and therefore perhaps somewhat more controversially, we also have this S8 tension, which essentially concerns this S8 parameter that measures the amplitude or describes the amplitude of weak lensing signal. And here, Planck predicts this S8 parameter to be higher than what is measured by weak lensing surveys. And so in light of all of these tensions or discrepancies, it makes sense to look at galaxy clustering and ask where galaxy clustering is in all of this puzzle. So galaxy clustering, as we know, is perhaps the most powerful low redshift probe that we have available. And therefore, hopefully it will be able to provide us with some answers or insight. Right, so the measurements that we're using come from Sloan Digital Sky Survey that obtained the most detailed 3D map of low redshift universe. And of course, this is not something that I can keep saying for long, because we all know that with DESI, we will have something orders of magnitude greater. But until they have analysis of year 1 out, I'll still show this video and say that Sloan was great. So here you're just seeing a fly through the Sloan survey. And the data sets that we're using are coming from BOSS and EBOS. So BOSS is the Baryon Oscillation Spectroscopic Survey. It was completed in 2015, and it consists of 1.2 times 10 to the 6 galaxies covering redshift ranges of 0.1 to 0.75. EBOS is the extended Baryon Oscillation Spectroscopic Survey, and while it has multiple parts to it, here we're only using the quasars. So that is in total 1.5 times 10 to the 5 quasars covering redshift ranges of 0.8 to 2.3. So what we do in this work is we present full shape of EBOS quasar clustering analysis. We combine this with full shape of BOSS galaxy clustering wedges, which are reanalyzed with an updated model for power spectrum and bias modeling. Our goal is to obtain combined large-scale structural constraints for the low redshift universe, and we do so by complementing our clustering measurements with weak lensing and clustering measurements from dark energy survey year 1 data release. And finally, we also look at some simple extensions to the standard lambda CDM model. And particularly, we're interested in what happens when we allow dark energy density to evolve. Right, but before we get to results, I just want to say a couple of words on how it is that we actually go from measurement to constraint. So how do we get our cosmological parameters? So our clustering measurements concern the 2-point correlation function. And this is the main observable. You can see what it looks like here. It represents the excess probability of finding galaxy pairs separated by a certain distance. And immediately you will note this feature, the baryon acoustic oscillation peak. And that, of course, is just the signature of pure combination universe when baryons and photons were coupled together and competed with each other. And today, at this day, we just have this excess galaxies found at this distance that refers to the distance that the acoustic waves traveled until baryons and photons decoupled again. And by measuring this baryon acoustic oscillation peak parallelly and perpendicularly to the line of sight, we are able to use it as a standard ruler and obtain constraints for the Hubble parameter and the angular diameter distance, but of course, in terms of the standard ruler. In addition to this, the 2-point correlation function also carries information about the structure growth, and it does so through redshift space distortions. So redshift space distortions happened due to galaxies having their peculiar velocities on top of the velocity that they have due to the expansion of the universe. So as galaxies move from underdensities towards overdensities, they have this additional peculiar velocity, and the contribution of the peculiar velocity along the line of sight also introduces this additional redshift shift or redshift contribution. And that results in an anisotropic pattern of galaxies observed in redshift space. And this can be seen, I think, perhaps most clearly when looking at the galaxy clustering wedges. So here I'm showing the galaxy clustering wedges from BOSS. And clustering wedges is just a 2-point correlation function measured in different angular directions. So here in orange, we see the clustering wedge measured perpendicularly to the line of sight, in blue, parallel to the line of sight, and in green, in a direction in between. And you can see how, of course, in these different directions, the amplitude changes, and that is due to these redshift space distortions. And we're able to fit this change in amplitude, and it can be described by the combination of linear structure growth rate and the density field variance. And normally, this is the parameter used for that is sigma 8, but really a much more appropriate way to describe this would be sigma 12, but I will get to this in a moment. The point being that normally, or I guess quite commonly, the information content of 2-point correlation function is summarized in these 3 summary statistics. So it is possible to just fit for the BAO peak and the redshift space distortions and leave out the rest of the information behind. However, an alternative way to analyze the 2-point correlation function is to perform the full shape analysis. So here, the entire measurement is modeled and fit. And in this case, we're able to extract the whole information carried by the 2-point correlation function. And also, unlike the summary statistics, we have to fit the BAO peak and the redshift space distortions of the same cosmology, which might not necessarily be the case in the summary statistic analysis. So the full shape analysis is what we want to perform here. So we want to fit our measurements and go directly to the parameter constraints from that. All right, so as I said, we're fitting measurements from Sloan Digital Sky Survey. So first, we're using BOSS clustering wedges measurements coming from Sanchez et al. And we're using the low and the high redshift bins only to avoid overlapping. And as I mentioned before, the clustering wedges are just the 2-point correlation function measured in different angular bins. So it's just a way to express the anisotropic information carried by the 2-point correlation function. For EBOS, we're using quasar clustering multiples. That's just one redshift bin covering redshift ranges of 0.8 to 2.2. And these are the measurements from Hu et al. And here we're using clustering multiples rather than wedges. And they essentially carry equivalent information. So when using clustering multiples, the 2-point correlation function is now expressed on the basis of Legendre multiples. So with each multiple having different angular sensitivity. So the monopole carries isotropic information, then quadrupole has some other angular dependence, and we're also using hexadecapole. So yeah, it's essentially the same information, but just expressed in a different way. Right. So as I mentioned before, we want to model the full shape of our measurement. And in order to do so, we have to have a model for the Fourier space equivalent of the two-point correlation function, the power spectrum. And for that, we kind of need three main ingredients. So first, we need a description for retrospace distortions. So we use the TNS model for this non-virial part. So this just describes the coherent infall of galaxies as they move from underdense to overdense regions. And we also have this finger of God correction, which accounts for the small scale virialized region contributions. And here we have one free parameter, this AVIR, which just describes the kurtosis of the velocity distribution. And this is nothing new. This is the retrospace description that has been used in all of the fiducial Boss analysis. Now, for nonlinear clustering prescription, we're using Respresso. And this allows us to obtain matter power spectrum predictions based on response function approach. And it's essentially a mix between a simulative and perturbative approach, and it requires kind of one measurement of the power spectrum from a simulation, and then it uses perturbation theory to predict what this power spectrum will look like in different cosmologies. And this has been tested for Boss-like samples to outperform alternative approaches such as effective field theory or GRPT. Finally, for galaxy bias, we used coevolution relations and one-loop galaxy bias expansion. So we have linear and quadratic bias, as well as the tidal bias parameters gamma 2 and gamma 2.1. And what we do here for the tidal bias parameters is we express them in terms of the linear bias, B1. So this can be done by assuming that we have a conserved number of tracers. Of course, in reality, that is not the case. However, it has been shown that this is a good enough approximation, and it works, again, for samples like ours. And it allows us to reduce the parameter space sample and obtain tighter constraints. So here, these coevolution relations are an update for both Boss and eBoss analysis. And I forgot to mention this Respresso approach was the same what was used for eBoss fiducial analysis. However, for Boss, this is an update. Right. So that's enough about modeling. Now, a very important part of our analysis is the parameter space that we are interested in. So the parameter space that we define is essentially related to this problem of defining parameters or units through H. So as I will illustrate and explain what the problem is right now. So as different probes recover different posteriors for Hubble parameter H, any parameter that is defined through H will be averaged over a particular posterior of the particular probe. So here in the top panel, I'm showing the posteriors of H recovered by some of the probes used in this analysis. And in the bottom panel, I'm showing what physical distance 8 megaparsecs over H will correspond to for these different probes. So if we take a look at kind of two extreme cases, for Planck, that measures H extremely well, 8 megaparsecs over H correspond to physical distance of 12 megaparsecs, well defined. However, for a probe like weak lensing, which is not really sensitive to H, which has this really wide posterior, 8 megaparsecs over H correspond to a wide range of physical distances. So we can take one step further and see what happens when we use sigma 8. So here on y-axis, I am showing the density field variance as measured on different physical scales. On x-axis, I'm showing the physical scales. And here the shaded regions just describe the 8 megaparsecs over H posterior for these different probes. So once again, Planck measures H very well. 8 megaparsecs over H correspond to 12 physical megaparsecs, and it measures the density field variance at a well-defined scale. However, for probes like DES and to a lesser extent Boss, 8 megaparsecs over H correspond to a range of scales. And so when we're measuring sigma 8, what we're actually measuring is a weighted average of the density field variance. So it doesn't really describe the same thing when we're using these different probes. And I explained this for sigma 8, but we have similar issues when using any other parameter defined through H. So also relative matter or dark energy densities. And therefore, oh, I skipped a slide. Okay. Well, therefore, in this work, what we want to do is we want to focus on the physical parameters. So first of all, instead of sigma 8, we want to use sigma 12, and it's essentially the same parameter, but measured on the scales of 12 megaparsecs, so measured on a physical scale. And then instead of the relative matter and dark energy densities, we want to measure the physical equivalent, so the physical matter and dark energy densities, which should have been defined separately, but that's quite disappeared. However, an important note is that this physical parameter space is only what we're interested in for our constraints. So it's a tool for us to understand what our probes are saying, what they're constraining, what they're describing. Our sampling is still performed in the kind of usual CosmoMC parameter space. So the matter density, the baryon density, the STMC, spectral index, AS, and whenever we're using Planck, the optical depth tau. Okay, another quick note before we go to actual constraints. So for assessing agreement, we're using this suspiciousness statistic. And suspiciousness statistic is kind of an updated version of Bayes factor. So it is essentially the difference between a gain in confidence in dataset A when dataset B is added, and you have information ratio subtracted from that, where information ratio describes unlikeliness of two datasets A and B ever matching. And the idea here is that by performing this action, we get suspiciousness that does not really depend on the priors used. And the issue with assessing the consistency in a way that depends on priors is just that if we have a very, very large prior and our two data sets are kind of somewhat close, but not quite, 2 to 3 sigma away, they will look very, very consistent in relation to this wide prior. And therefore, suspiciousness kind of tries to remove these two wide priors and assess consistency in a prior independent way. So for Gaussian posteriors, suspiciousness follows chi-square distribution. However, in practicality, we calculate suspiciousness just from this variance of likelihoods. So an important note again here is that you don't need to define a specific parameter space to assess suspiciousness. It just uses essentially the goodness of fit. Okay, and finally, we can go to the results. So let's take a look at BOSS and eBOSS on their own first. So here I'm showing the constraints for lambda stadium, for eBOSS in brown, BOSS in this blue, the combination of the two in green, and Planck in dark blue. So as you can see also by eye, but also with suspiciousness, the data sets are in good agreement with each other. So BOSS and eBOSS agree quite well with each other, and the combination of the two are in a very good agreement with Planck, within 0.6 sigma. And if we are particularly interested in the clustering amplitude, you see that actually sigma 12 from the combination of the two is in a perfect agreement with Planck's prediction. And the sigma 8 value that we get is maybe a little bit high, but still everything looks pretty good. So everything looks great. However, we want to also perform another additional consistency test. And this is based on this evolution mapping idea proposed by Sanchez et al. So here, once we define our physical parameter space, we can divide our cosmological parameters into shape and evolution kind, depending on how they affect the power spectrum. So the shape cosmological parameters, as it says on the tin, describe the shape of the power spectrum, whereas the evolution parameters describe the amplitude of the power spectrum. So shape parameters are such as the physical baryon density, called dark matter density, or NS, whereas evolution parameters are like sigma 12, AS, or dark energy density. So a nice property here is that for fixed values of shape parameters, any combination of evolution parameters that lead to the same sigma 12 will result in identical power spectrum. And that is exactly true for the linear power spectrum and very close to truth for a nonlinear case. So what we want to do here is we want to take Planck's constraints on the shape parameters and impose them as priors on our clustering analysis. So we're kind of forcing our clustering data sets to choose cosmologies with power spectra whose shape matches the one preferred by Planck. And then we want to see whether we also recover consistent amplitudes. So here's the result of this test. So in gray, I'm showing the white prior analysis, the results you saw in the previous slide. In green, I am showing what happens when we impose these informative priors. And in blue, I'm showing Planck. So if we take a look at the matter and NS constraints, you can see that they match Planck exactly. And this is by design. And if we then take a look at the evolution parameters, we also see that everything is quite consistent. So the dark energy densities may be recovered to be a little bit higher than what Planck prefers, sigma 12 a little bit lower, but overall everything is looking pretty good. And a nice aspect of this test is that we can only measure tension or consistency in parameters that we can constrain. And by imposing these shape priors, we are increasing our constraining power, especially on parameters like dark energy density, which isn't well measured really. So everything is looking good here. Our consistency test is passed. Now let's look what happens when we add recleansing. So here we are adding 3 times 2-point measurements coming from DES year 1 data, and the constraints of that on its own are shown in light blue. BOS and EBOS again shown in green, the combination of all the redshift probes shown in orange, and Planck in dark blue. So overall, over the whole parameter space, we see that adding DES does slightly degrade the agreement with Planck. So now our suspiciousness between BOS, EBOS plus DES and Planck shows agreement of 1.5 sigma. So slightly worse, but still not really anything to write home about. However, there are several interesting things that we see here in the physical parameter space that I would like to point out. So first of all, if we look at this physical matter density sigma 12 parameter space, we see that recleansing on its own is in an excellent agreement with Planck. And so is clustering on its own as well. And it's just the combination of the two that result in a contour that is slightly below Planck. And that's in comparison to the usual parameter space, when with relative matter density and sigma 8, you see this familiar banana and the Planck contour being high. And when we compare the two, what we can say is that for these data sets, the discrepancy in the matter sigma 8 space for recleansing only appears due to the use of these megaparsec over H units. But of course, you might say, Agne, you told us that suspiciousness doesn't even care about the parameter space that you use, and adding DES degrades the agreement, so clearly something is going on here. And indeed, that's true. So if you had a keen eye, you might have noticed that instead, this slight discrepancy appears in a different parameter subspace when we use the physical parameters. So now we can take a look at this AS sigma 12 parameter subspace that connects the initial amplitude of the power spectrum with the amplitude that it should have today. And here, both recleansing on its own and its combination with clustering are in some disagreement with Planck contour. And I think in this parameter space, this disagreement can be interpreted very straightforwardly. You don't need to think about any kind of recleansing amplitude parameters. So here, for a selected value of sigma 12, Planck prefers a lower value of AS, so more total structure growth than the large-scale structure probes. And the significance of this difference is around 2.5 sigma, so it's very similar to what we see in S8. So that's very cool. And just to note, this is not something that we would see if we were to use sigma 8, because when we're using sigma 8, we have this averaging over the posterior of H0, and this tight correlation between these two parameters gets kind of washed out, essentially. Right. So there's something happening with total structure growth, perhaps the amplitude of the power spectrum. Let's look what happens in our consistency test. So here again, sorry, in gray, I am showing our initial white prior analysis. In orange, I'm showing what happens if we impose Planck shape parameters, Planck shape posteriors as our informative priors in the analysis. So what happens now is we see that the shifts that we see in the evolution parameters are somewhat more significant. So sigma 12 gets recovered roughly 1.9 sigma below Planck value. AS gets recovered 1.2 sigma below Planck value. And the dark energy density seems to be, the preferred value is 1.7 sigma higher than what Planck finds. And again, this is not really very significant, of course, but qualitatively, this is very consistent with what we saw with our main analysis. So if indeed Planck prefers more total structure growth than the low redshift probes, it makes sense that it also prefers less dark energy density because, of course, dark energy stifles the structure growth. So it's nice that what we're getting seems to be consistent with what we saw before. And just one note on assessing consistency in general. So we say that we are comparing Planck with low redshift probes. However, none of these probes really measure anything at redshift 0. And redshift 0 is what we're looking at and where we're comparing our constraints. And so when we're looking at any quantities that evolve with redshift, the agreement between constraints may also evolve with redshift as well. So here I'm just showing this example for S8. So here I'm showing the constraint for BOSS, EBOSS, and DES in orange, and for Planck in blue. And I'm just looking at the constraints at different redshifts essentially here. And you see that at high redshifts, the two sets of probes are very consistent, and it's only at redshift 0 that they become inconsistent by roughly 2.5 sigma. However, there is no real reason why we should look at redshift 0. It's as arbitrary as any other redshift. And if we were to extrapolate this even further in the future, we would see an even greater discrepancy. And so I think that when looking at these separate single parameters, we must bear in mind that still the comparisons that we're making and the numbers that we are attaching to them are fairly arbitrary. Okay, but enough of that. We saw that Planck prefers slightly more total structure growth and that this is maybe related to dark energy somehow. One important note is that dark energy density is not a parameter that any of our probes measure well, and therefore we cannot really, well, we wouldn't be able to see tensions even if they were there because we can only measure tension in something that we can constrain. Nevertheless, we know that we do assume a lot about dark energy. For example, we assume that it's constant in lambda CDM. So let's look what happens when we do not assume that, when dark energy is allowed to evolve and the equation of state parameter W is not fixed to -1. Well, what we find here is that, first of all, our physical parameter space is super duper useful in these kind of cases. And I will illustrate this with WCDM. So here first, let's take a look at our usual regular parameter space. And here I'm showing BOSS and EBOSS in light blue, Planck in dark blue, and the combination of the two in red. And here we see that Planck is no longer the super constraining, amazing probe that we all know and love. It has this really large extended contours. And of course, that shouldn't come as a surprise because now we allow dark energy density to vary. And as Planck measures CMB at really high redshifts, it really struggles to know what dark energy is supposed to behave like now. And so if we do not provide any prescription, of course, it does not constrain the values of these parameters today anymore. And this can be seen very explicitly if we look at the physical parameter space. So we know that the value of H0 today is mainly determined by the sum of physical and dark energy densities. And you can see that the physical matter density is still constrained extremely well, and it is the dark energy density that is the cause of these extended contours. However, very importantly, Planck does actually also constrain the clustering amplitude today, sigma 12. And that might seem a little bit unexpected at first, because if you looked at sigma 8, you saw this really wide contour and you thought, oh yeah, well, I guess Planck doesn't know what clustering amplitude is supposed to be today. However, the point here is that only certain combinations of W and dark energy density are allowed. So you see that there is this really tight degeneracy that sets the angular diameter distance and sets the value of sigma 12. And just to really drive this point home, I want to compare here sigma 8 and sigma 12 for Planck in lambda CDM in dark blue and in WCDM in green. And you can see that actually Planck does not just constrain sigma 12 extremely well, it actually constrains it just as well as it does it in lambda CDM universe. And therefore our work provides the first Planck constraint on the power spectrum amplitude today in cosmologies with varying dark energy density. And I think it's super exciting because
Sorry, Agne, if I can just jump in there, you have a very unphysical value for W, right? It's peaked on W equals minus 1.5, which would tell you that there's a turning point in the Hubble parameter, which is a violation of the null energy condition. So it's very difficult to read into these constraints. We've discussed this offline. Yeah. We've discussed this over email. So this is good to basically explain this to the audience. Thank you.
Yeah, so thank you for making this point. Indeed, the priors that we used for our parameters, for our cosmological parameters, simply it's the same, well, yes, more or less the same as in the original Planck analysis. But yes, as you pointed out, it could also include unphysical values. But the point that I'm trying to make here is, I guess, the constraints that we're mostly interested in come with combination of clustering, and that does shift W to the physical values. And another thing is that here I'm more interested in exploring, I guess, how the physical parameter space allows us to interpret certain things. And the constraint on sigma 12, as we see, does not in fact depend on W, right? So any point in this degeneracy, any combination of W and dark energy density will result in the same sigma 12, or at least very similar sigma 12. So in fact, most of the conclusions that we're making here don't really heavily depend on this prior on W. But indeed, it's something that is helpful to bear in mind that
if I can add something, actually, okay, there could be some theoretical model from Frost principles that give an effective dark energy equation of state that is in the unphysical region, so it's phantom, but they are physically motivated. So it makes sense to explore the unphysical region because it could be just an effective phantom dark energy. Okay, we can discuss this later. I think, okay, let's keep questions after the talk.
Yeah, okay. Yeah, so this is an interesting discussion, but I think also, I guess it's important to point out that a lot of the conclusions that I'm making actually are not super dependent on W, because as we see, Planck constrains sigma 12 perfectly fine, even when W is allowed to evolve. And again, when we compare this to sigma 8, we see that, of course, with sigma 8, we don't get the same result, and we get this really, really wide constraint. And again, this is not because Planck does not know what the clustering amplitude is. It's because it doesn't know what scale to measure it on. So if we tell it to measure sigma 8 at 8 megaparsecs over h, it just doesn't know what 8 megaparsecs over h correspond to in these cosmologies with varying dark energy density. Right, so that's all really cool. In general, all of the constraints that we get are actually consistent with lambda CDM, so I guess that is slightly less exciting. And we see that the value that we recover of sigma 12 in these WCDM cosmologies is shifted to slightly higher values. So it doesn't really help us all that much with the tension in the structure growth. Another interesting thing that we can explore is what happens if we also allow the curvature to vary in addition to varying W. So Planck is known to prefer a closed universe, negative curvature at 2 to 3 sigma significance. So let's look what happens if we look at our physical parameter space. Well, what we see here is, now I'm just showing Planck constraints on their own, and in the dashed line, I'm just marking the 0 value. And what we note here is that using the physical curvature density allows us to obtain much more precise constraints than we had before. So if you look at the errors, they're like order of 10 better for the physical curvature density. So what we measure is essentially the same thing. We see a negative value for the curvature density. However, due to this not averaging over H0, we get a much more significant result. So we see that the value of the curvature density that we recover is actually 4 sigma away from flat universe. However, there are some caveats here. So when we add clustering to this mix, we see that within these curved models, clustering and Planck do not really agree with each other. They are in tension. And I guess this is most obviously seen in this W dark energy density plane, where the two sets of contours really are barely touching each other. And as we saw before, this parameter subspace is what defines the value of sigma 12. And indeed, if we also look at sigma 12, we note that now Planck prefers a much higher values of sigma 12, and it's really quite inconsistent with clustering. And in fact, this is the greatest shift in sigma 12 values that we see in the different models considered. Anything else I have to say here? No, I guess this is something that was also known before, this discrepancy between clustering and Planck in the curved universes. However, here we show that varying W does not really help us much. It doesn't reduce this disagreement. And here in physical parameter space, it's quite clear why, right? Because varying W does not change our measure on the clustering amplitude today, as we saw before. And if they are discrepant in curved universes, they will be discrepant. Is that a question? I guess not. Sorry. Yeah, so if they were discrepant in the universes without varying W does not really do much to get these amplitudes closer to each other. Okay, and this is all also quite closely related to this A lens problem. So again, as you probably know even better than I do, there is also this issue with Planck kind of showing more lensing in its temperature spectrum than you would expect. And if we vary this A lens parameter that describes the amount of lensing expected, here I'm showing what happens to the Planck contour when we do so in light blue. We see that that brings Planck closer to both flatter universes and lower values of sigma 12. So yeah, essentially, this is again known, but just kind of an illustration that indeed all of these problems are related together. Yeah, and that is kind of all that I had to say, because and these are my conclusions. So overall, we do find that within the standard model, everything is very consistent. So the full shape analysis of clustering measurements is consistent with Planck, and they still show good consistency even when DES is added. When imposing prior on the cosmological parameters that define the shape of the linear matter power spectrum, we find a preference for higher dark energy density by the low redshift datasets as compared to Planck. But again, this is not super significant. We also show that Planck does constrain clustering amplitude today, sigma 12, even when dark energy is allowed to involve, as long as physical parameters are used. And we also further show that Planck constrains physical curvature density parameter, omega k. But this cosmology is incompatible with clustering data. And our final constraints overall, other than this curved universe, recover the standard model parameter values. And yeah, this is all that I had to say, and I'm happy to answer any questions now. Thanks.
Thank you, Agne. Okay.
Thanks.
Okay, do we have any questions? Yeah. Ellie?
Yes, please. Go ahead.
Okay, great. Thanks for the nice talk. I'm multitasking at the moment, so I could only sort of dip into it. Okay, so let's start with some very simple observations that you can make. If these tensions are physical, lambda CDM is breaking down. So it's not systematics, lambda CDM is breaking down. Any dynamical model that breaks down, its fitting parameters have to evolve with time. This is very, this is again a very safe statement in physics. Now in lambda CDM, what would that mean? That means that there has to be evolution in the fitting parameters with redshift. That has to happen at some redshift. Again, these are very, these very simple statements that have to be true if the model is breaking down. Now, if that happens in the late universe, there's nothing to guarantee that H0 or omega m0 are constants. Basically, it means that they should evolve with effective redshift if the model is breaking down. And now, so I guess the question here is basically, as we go to larger parameter spaces, as we go beyond H0 and go beyond omega m and go to W and go to omega k, and maybe even what other extra parameters we have, are we basically seeing hints of that evolution?
So you mean evolving equation of state or evolving densities, or?
You could interpret it as an equation of state. You could interpret this many different ways, but essentially, like I'm suggesting that basically, look, okay, so you could take like the Pantheon sample or any supernovae sample and basically bin it into low redshift and high redshift and fit the cosmological parameters. And what you'll find is basically the cosmological parameters that you get in the high redshift subsample are, the H0 is lower and omega m0 is higher in the Pantheon sample. And I can give you some sort of mock analysis that would basically argue that that's the right result. And it's nothing to do with systematics, and it's basically more to do with the model.
Right.
Now, so I guess the question here, these are maybe more comments than anything else. I mean, why are cosmologists not taking it seriously that the model is breaking down and that H0 and omega m0 could be evolving with redshift?
Well, I don't know if I can answer for all cosmologists.
So let me put it this way. So what people seem to do is they have samples, but never really, those samples they have an effective redshift. So everything you're discussing has an effective redshift, right? If we had enough data sets at different redshifts, we could sort of bin them.
For sure.
And then we could basically, decompose everything, and we would see that, there's this evolution, and we would essentially confirm that the model is breaking down. And if we didn't see this evolution, we would sort of say, oh, the model's fine, right? There's nothing to see there. This is some sort of systematics.
Yeah. Sorry.
But with some of these large data sets, it's difficult to do that, right? So for example, with cosmic shear, it's difficult to do that. With BAO, it may be difficult to do this, but here with supernovae, you see this. With observational Hubble data, you see it as well.
Yep.
Maybe let me just ask you: is this feasible? Can it even be done?
So I think for clustering, indeed, that probably would be the best thing to do, right? To actually look at the effective redshifts of the samples. But then for probe-like recleansing, it's actually non-trivial to define what is the effective redshift, right? Because for shear, the lensing kernels that are being used, they are really I don't know if you've ever seen them, but they're basically, they stretch over ranges of redshifts. And therefore, like, it's really, I don't know if there is a way to describe an effective redshift, since it's an integrated effect over, all of the matter that's between us and the lens or the source galaxy. So I think it's not super clear what to do then. I think for clustering, for sure, these are very helpful. And I think very often, in particular, when describing the growth constraints, I think it's quite common to quote them for each of the effective redshifts of the sample. So you will often see this diagram of redshift and the value of F sigma 8, and you will see the measurements from different clustering samples that you have. So quasars, Iono-Lyman alpha, red galaxies, etc. And I do think that these are extremely informative, and they're much more helpful perhaps than just forwarding everything to redshift 0 and comparing it there. But then if you want to compare it with different data sets, and in particular with cosmic shear, I don't know if there is a straightforward way to do so.
Actually, it's something I had a quick look at. I take your points. I completely agree with them. Cosmic shear is sort of difficult because it's a series, it's over bins, but HSC seems to have a slightly higher effective redshift than DES. So in principle, all their bins are kind of shifted to higher redshifts. So in principle, you could do this study, but the data would want to be very, very good quality, right? And it's probably years off in cosmic shear, right? Yeah, I mean, I agree. It's difficult to know what to do with cosmic shear, right? But again, the key point is that if the model is breaking down, if the tensions are physical, then you need to see evolution in H0 and omega m0 at some redshift.
Yeah.
And the logical place to look for it is the late universe. Okay, thanks very much for the talk. Thank you.
Thank you.
Okay, do you have any other questions? Marco, please.
Hi, thank you for the great talk. I had a curiosity, which I never get to ask. I am confused about where the constraining power on H comes from, right? You were showing the posteriors from Bose, which showed, some sort of 10% constraint on H naught, which then you use to calibrate S12 and so on. But these are all dimensionless measurements, right? And H naught is dimensionful. So the order of magnitude thing should be that there's no constraint on H naught. So
Right.
what's physically doing that?
Yeah, so this essentially comes from the BAO measurements. Let's go to the start. One moment. Nope, I think. I went too far. Oh no, okay, sorry. My laptop could not handle all the slides and it's now frozen. Okay.
Okay.
Come on, we can do this. Yes, okay, here we go. Yeah, so essentially H naught information comes from the BAO feature, right? So we fit it parallelly and perpendicular to the line of sight. And really, of course, what we get, we need to compare it with something because as you say, it's kind of dimensionless on its own. You can just say, okay, well, it's here. And what we compare it with essentially is this, the sound horizon distance at the redshift of decoupling. And again, if you do the BAO analysis on its own, you do have to usually assume some sort of value for that. So normally people take Planck's measurement, and there has been some work on how much the constraints depend on that, and do we get any inconsistencies if we do not assume this, what happens? In full shape analysis, what serves as a measure of that is essentially the baryon density. So this is something that clustering analysis do not really constrain on their own. So we do have to impose a somewhat informative prior. However, the width of the prior that we use is, I think, something like 25 times wider than Planck constraint, if I remember correctly. So that's what serves as a way to measure the sound horizon distance. And then through that, we are able to constrain H naught and through measuring the BAO.
Okay. So can you remind me, are you using BBN priors basically? So BBN is the calibrator.
So here we're using essentially Planck prior, but 25 times wider. And I don't remember precisely how that compares with BBN, but I guess it is similar.
Okay, I see. Yeah, so which I think it's fair to say that, the BAO measurement is not constraining H, right? So basically,
it's a combination, yes, of H and the sound horizon distance.
Yeah, so basically you're using an arbitrary prior to calibrate for the absolute calibration of the measurements, right? So how that impacts considerations on S12 or sigma 12?
Well, so while our prior is, informative in the sense that we do not constrain the baryon density itself, it's really, really wide. So all of the other constraints that we recover are actually well within their priors. I guess it would be interesting to look at how different baryon priors affect the constraints. But I think also in previous analysis, it was quite common to use either fixed baryon density or much, much narrower priors on that. And I think, and the results that we get are very consistent, both errors-wise and mean values-wise, with these previous analysis. So while we didn't perform this check ourselves, I don't think it actually has such a great impact on the overall parameters recovered.
Okay, thank you.
Okay, thank you. Any other questions?
Hello, I have a question. In your talk, you have used some different redshift. As I know, we are using the redshift for measuring the distance. So, what is the difference between the effective redshift and the other redshift you are using in the?
Well, we're not using a particular redshift. I just described the redshift ranges that our samples kind of cover. And well, okay, I guess the measurements are calculated at an effective redshift, but then that is the effective redshift. So I'm not sure.
Is the effective redshift is same as the normal redshift, or is there any difference between the effective and?
So it's the effective redshift of the sample, of the entire sample of the galaxy. So it's kind of where the constraining power is the strongest, essentially.
Okay. Thank you.
Thanks.
Okay, any other questions? Okay, I have a question. Did you investigate the effect of having a total neutrino mass? Because I think that here you are just using the default.
Yeah, so we're just using the fixed neutrino mass here. We looked at what happened when we varied neutrino mass together with W, but it didn't really change things so much because, well, clustering, I can, I guess, even show the plot. I think I had it somewhere, but again, it will be many slides away. But yeah, essentially, our clustering measurements are not really good enough to constrain the neutrino mass on their own. And in particular, and in particular, the constraint that you get when varying dark energy, it's even looser than what you get normally. So yeah, I don't know, it's not very conclusive. I think that all of the values, it didn't really didn't result in any more significant shifts, or I don't know, nothing crazy there. Okay. I don't have anything very insightful to say about neutrino masses, unfortunately.
Okay, so nothing changed about tensions, because okay, neutrinos usually are one of the suggestions to solve the SA sigma 8 tension. So
right, so I think actually like one thing is that we should probably look at this in lambda CDM, but then since we were kind of looking at extensions plus with varying W, yeah, that I guess did not help to
okay.
get the clear picture. Yeah.
Okay, any other questions? No? Okay, so thank you, Agne, again.
Thank you. Thanks for inviting me.